end windings. Basically, we also observe another phenomenon that some winding had the temperature go up and down within several days, and I'll show the data later. But all the changes are less than 20 degrees F, so nothing to be excited about once again. We believe that the scatter temperature, water temperature, will be showing the aggregate of all the windings. Now, we are concerned about the individual water cooling conduit, whether the flow rate is the same. By the time it comes out as an aggregate, most of the time the scatter system show that they are quite uniform and stable. Now, I don't think there is any concern at the Turkey plant, but I want to show you when we examine the data from China that one or two of the sensor sensing temperature very close to 100 degrees, and that is a little bit alarming. And we intend to discuss with the plant about this finding, because without knowing it, they will be operating as if there's nothing happening, and one of the end winding will be subjected to this elevated temperature for prolonged period. The weakest link will become affecting them, the generator overall. In general, from the vibration data, you can even see the loading pattern from day to evening. So you can see it quite regularly. And then we have already identified 5 channels showing some initial looseness, but not a big deal. Okay, but the largest amplitude compared with the smallest amplitude is a factor of 2. But all readings are well below even the 2 mil, which is the baseline value, not to mention alert limit or even the shutdown limit. That will be far away. So even the temperature is well within the safe limit, because what we consider to be alert will be 100 degrees C, not 100 degree F. Okay, so the Turkey plant is looking good and is running quite well. Now, the story might be a little bit different in the China plant, and can see a totally different pattern of operation. I cannot say that it's operating like a base load, but the loading swings periodically, almost daily, well, within the day, and it's something that we don't understand, but it's affecting the vibration pattern. So again, we identify some slight looseness, okay, some slight looseness based on the comparative reading the vibration of the various channels. So we got four windings on the top of the exciter end, okay, that is we like to comment on. We got another 4 windings in the bottom of the turbine end that is getting loose. Okay, we believe that this looseness is introduced by rapid and frequent loading change. Okay, and so I would like to also show you some temperature effect. So from day to day, there is also temperature changes. So this is something that I like to correlate with the water outlet temperature. Okay, so what happened in the China plant? Before we install, the plant engineer explained to us that they have some concern about a location where is the phase lead, and they saw some burnt mark there, and therefore they would like to dedicate 2 of our sensors to place at the location where where they witness the burnt mark. So accordingly, they put channel 3 and channel 4 there. And I would like to show you later on. And they are quite okay. These sensors are showing after the maintenance, they rework it, and everything seems to be okay. Now, if you look at the turbine end, we got seven channels already installed. So just to remind you that all our sensors have been calibrated before they leave the factory, and this is as part of this is a certificate of conformance that we issue. And you see each of our sensors has serial number, and what we try to do is keep the sensor made from the same batch. Okay, our TG gas structure is modular, so each laser is being shared by 8 sensors. So we try to make sensors that are consistent within the same module. So you can see that they have the same batch number and different serial number. Now, the calibration shows that we're trying to accomplish 100 millivolt per G, or if you like, displacement, and that will represent 10 millivolt per micron. Okay, the degree of accuracy we can accomplish is plus or minus 1%, shown here. Okay, so 99 millivolt, 101 millivolt, most of them are 100. So the accuracy as you read it on the amplitude is plus or minus 1%. So with that, we place it on all the end windings, and they are showing different value. So we believe that this is not due to the sensor themselves, and they are actually showing the actual vibration amplitude of the particular end winding. Now, the table shows they have various loading, 600 megawatt, 450 megawatt, 360, and 300 megawatt. And we are fortunate enough to collect data for 2 years. So I'll be showing you the effect of this rapid loading change on the growth of vibration amplitude. Okay, so I know it's very difficult to look at all these numbers in detail, so we may use some plots. Here it is. So very clearly, the vibration amplitude is load dependent. But there is also a threshold. So below 360, it doesn't seem to matter. You have data from 300 megawatt, and this part is relatively flat. And on both sides, is showing the similar phenomenon. Now, remember the engineer told us he's very concerned about the phase lead, and he put 2 sensors there. So channel 4 and channel 3. Channel 4 green, channel 3 blue. They are not a big deal. So it's no longer vibrating. Actually, the one is vibrating most, okay, is channel 1 and 2. Okay, 60 micron, also very small. Okay, is consistent or also on the other end, 16 and 15. So here you can see the vibration amplitude is very much loading dependent, and is in fact is fairly linear. Beyond the threshold, there's a threshold phenomenon starting at 350 megawatt, and then after that it tracks quite linearly. Okay, here is more interesting because we plot all the sensors, 16 of them together. And then what we do is we group them by different loading levels. So if you look at the top two curves, they represent 600 megawatts. They are from 2 years. So you see the blue on the top is actually from 2011. And then the 2012, the pink has actually grown. Okay? So this is showing up on 15 and 16. Okay? The same pattern also repeat itself when the loading is decreased at 450. So in 1 year, okay, they have increased the amplitude of the vibration from, say, 50, 60 to 70 now. So can you expect the same thing to continue in the years to come? And I think this foretells a little bit of a problem. Now, I also want to explain to you that the pattern where the sensor showing the various amplitude is consistent. Okay, there is a V shape here at 600 megawatt, and the same V shape is showing up at 450 megawatt, and then eventually at 360 and 300. The two loading level are clustered together, showing you that basically makes no difference. Now, I would like to discuss with the plant engineer about this threshold phenomenon. It is kind of new to me. So for now, in terms of condition monitoring, you look at the top of the V curve. These guys, 3, 4, 5, and 15, 14, 15, 16. And these are the sensitive spots. And they are showing growth from year to year. So since part of the failure mechanism of the generator is that looseness enable the vibration amplitude to grow, so we watch the hop. So on the turbine end, we recommend watching channel 14, 15, and 16. But for the time being, everything is okay because the baseline value is 2 mil. It's actually not alert. Its baseline value is 2 mil. And then we will alert only when it's 2 times that, 4 mil or 100 micron. And on the exciter end, it's the same. We have channel 1, 2, 3, 4. These are target for a little bit more attention. So remember, the plant engineer indicate where the last time they do maintenance, they open up, they found burn marks on the face lead, and then they place sensor channel 3 and 4 there. Okay, I would like to show you that they are okay, and I have data for that. Now, let's look at the time domain.